Now, we look at how to use the second derivative to locate the local maximum and the local minimum. Before that, let's do some observations. So we have this concave up curve. At this point, if this is the corresponding to x value is c, okay, and f of c would be the local minimum, right? Local mean. So since this curve is concave up near the c, okay, when x is near to the c, it's concave up. The curve is concave up. So that means the second derivative at c should be greater than 0. Right? And now let's look at another one. This is the curve. At this point, which corresponding to c, this would be f of c would be a local maximum. And we know the curve near the c, when x is near c, the curve is here, which is a concave down curve. Concave down, that means f double prime, the second derivative f at c should be less than 0. So this one gives you the idea for the second derivative test. So this is the theorem. Second derivative test. It says let c be a critical point or value of this function f of x. Then if the second derivative at c is positive, so that means concave up nearby, then the function values at c is a local concave up, so local minimum. 2. If the second derivative at c is less than 0, then f of c is less than 0. That means nearby is concave down. So this would be a local maximum. 3. If the second derivative at c equals 0, then the test fails. So you have to use other tests. For example, you use the first derivative test to determine it's a local maximum or the local minimum. So from the first derivative test, the second derivative test, you can see that the first derivative test, we need to know the increasing or decreasing on both sides of the critical points, right? For the second derivative test, you just need to plug in the critical values into the second derivative to see it's positive or negative to determine it's a local maximum and a local minimum. But if the second derivative equals 0, so we cannot use the second derivative test. So we have to go back to the first derivative test to see that both sides is increasing or decreasing on both sides of this point. Okay, we still use an example. We use the same example as we studied the concavities. This example, that's h of x equals this polynomial. H of x equals 3x to the fifth minus 5x cubed plus 3. So you see, we want to use the second derivative test to determine the local maximum, local minimum. So you see, this C must be a critical point. So the critical point, we have to take the derivative, right? To find the critical points or critical values, we have to take the first derivative, which is 15x to the fourth minus 15x squared. If you factorize it, this would be 15x squared, x squared minus 1, so it's x minus 1, x plus 1, if you factorize it. Then, since this one exists everywhere, so we just need to set the derivative equals 0. So the derivative equals 0 is 5x squared, x minus 1, x plus 1 equals 0. So don't forget, you cannot erase this 15x squared. The reason is x squared. When you divide by x squared, that means you assume this x squared is not 0. However, x squared is 0 is the solution for this one, right? You have x squared, x equals 0, so this term contribute x equals 0. And this term contribute x equals 1. This term contributes x equals negative 1. So you have 3 critical points. Critical points. Then we just need to plug in what? F at sorry, not F, it's the H double prime. So we still need to compute the H double prime, right? The H double prime we have computed already, which is 60x cubed minus 30x equals, which is 30x times x squared 2x squared minus 1, right? So we need to test. Let's plug in 1 first. So we plug in 1, so this would be what? Which is positive, right? 30 times 1 times 2 times 1 squared minus 1. So this is positive, right? So that means concave up, right? So by the second derivative test, then we can see this H1 is so concave up, so local minimum. This is the second derivative test, right? So plug in -1. So this would be 30 times -1 times 2 times -1 squared minus 1. So it's negative, right? So that would means h of -1 is a local maximum. So be careful. Here is the second derivative. Here is this original function. Original function, right? Here is original function. We'll still use the second derivative test. But if you plug in the 0, it would be 30 times 0 times 2 times 0 squared minus 1. So this would be a 0 would be equal to 0. So that means the second derivative test fails. Okay, so you have to use our first derivative test. So let's locate to see the result. So let's locate our critical values on our domain. 0 here, -1, and 1 here. And this one divide our interval into 4 parts. Here we can see this one is f prime. So we want to use the first derivative test. So go back to first derivative test. So we need to plug in to the first derivative, so you will see this one is positive. So here is positive, the first derivative, so it's increasing. And here we can plug in negative 1/2, right? Then you will see it's negative, so here is negative. Then this is decreasing. And here is, you can see positive, plug in 1/2, which is positive. So on this interval, the first derivative is positive. Sorry, it's negative. Negative. Then here is h prime of 2. It would be positive. So h prime at here is positive, so it's increasing, right? So you can see that negative 1 is the local maximum, right? So here is the second derivative tells you that the maximum, local maximum h of negative 1. And 1, so this is the concave term, right? Increasing, decreasing, the local maximum. And here is local minimum, right? So here the second derivative tells you that it's a local minimum. So you don't need to find the increasing and decreasing. But for 0, from the second derivative, we have no idea the behavior of the function on both sides of 0, right? We do have no idea. But from here, from the increasing or decreasing function, we know that on this side, which is decreasing, on the left side is decreasing, then goes through 0, it's decreasing again, right? It's decreasing again, so it's always decreasing on the interval goes through 0, so that means 0 is not a local maximum or local minimum. So we only have 2 local extrema. One is extreme 1 with h of 1, which is local minimum, and h of negative 1 is local maximum. So from here, h of 0 is not a local maximum or local minimum. Right. So in other words, sometimes you need to use both tests. Sometimes you can use the first test. Sometimes you can use the second derivative test, which is more convenient. But if you get a second derivative equals 0 at the critical points, then you have to go back to the first derivative test to see what happens, right? So it depends on you which way you want to use.